Hey, hello and welcome back everyone. We're just going to go through the worked examples for systems of first order, linear, homogeneous, constant, coefficient, ODEs. Still a mouthful, not much we can do about it. And we're really just going to go through two examples. Now, the second example will be a little bit special, a little different than what we've seen so far, but it won't be anything too terribly crazy. But yeah, aside from that, two examples, make sure everybody knows what they're doing before we move ahead. So first example, let's go ahead and solve the system of ODEs. I'm going to make our lives a little tricky and switch the variables up on us and call this y1 prime is equal to y1 minus y2, and y2 prime is equal to y1 plus y2. Then let's say that y1 at times 0 is equal to 1, and y2 at times 0 is equal to negative 1. So there's a system of ODEs. It looks like the variables in this case are the variables y. What we really want to do every time we're going to try to solve these systems of linear constant coefficient ODEs in first order. The order, by the way, I didn't really cover that in the last video. The order is just the total number of derivatives or the highest power of derivatives. Here we just have one derivative in each equation. You could imagine I could add derivatives if I wanted to, and that would be a second order equation there. So first order means that we're restricting ourselves to one derivative. Linear, I think, should be straightforward, is because we have a matrix which represents the equation. Homogeneous means that there's no forcing terms. So you could arguably add like 7 and you could subtract 6t or something like that. These would be inhomogeneous. It means to add some terms that are not multiples of the variables. And constant coefficients should be pretty straightforward as well. Because all of the coefficients we're looking in terms of here, 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 and here don't depend on time. So that's where all those words come from. What we're going to do is convert to vector form. And in converting to vector form, basically we're going to make the assumption that the vector y is equal to entries y1, y2, and maybe our matrix is equal to the coefficients. It looks like we have a 1, a negative 1, a 1, and a 1. So we're looking at 1, negative 1, 1, 1, as well as our initial condition, 1, negative 1 there. So converting to vector form, this is really turning into y as a vector prime is equal to the matrix 1, negative 1, 1, 1 against y as a vector. And the initial condition in this vector at time 0 is equal to the vector 1, negative 1. So now that we've written it in this form, we do have our solution formula that comes fairly straightforward. It says that's the solution given as a vector is the vector evolving over time, matrix exponential t minus the initial time. The initial time is 0. So t minus 0 times the matrix 1, negative 1, 1, 1. And I'll go ahead and just write that as e to the t matrix. T, 1, negative 1, 1, 1. And this all multiplies the initial vector 1, negative 1. So we just need to go ahead and actually solve for whatever that right hand is, compute everything here, and then we'll have our answer. So to compute e to the t 1, negative 1, 1, 1, we're certainly going to have to go through diagonalization. This will be ex e to the t diagonal, x inverse, where the x's have columns of our eigenvectors and the diagonal d has diagonal values of our eigenvalues. So we'll just have to go through diagonalization of 1, negative 1, 1, 1. As always with diagonalization, let's start with eigenvalues. So we're going to compute the determinant of 1 minus lambda, and then negative 1, 1, and 1 minus lambda. This will be 1 minus lambda squared minus negative 1, so plus 1. We're going to end up with 1 minus 2 lambda plus lambda squared. That's me foiling. Plus 1. Looks like we have lambda squared minus 2 lambda plus 2. This is equal to 0 for my characteristic equation, and I'm going to go ahead and use the quadratic formula to give me lambda is equal to 2 plus or minus the square root of 2 squared is 4 minus 8 all over 2. That's going to give me 2 plus or minus the square root of negative 4 all over 2. And because it's the square root of a negative number, there's going to be an I that pops out times the square root of 4, which is a 2. And so we'll have 2 plus or minus 2i divided by 2, also known as 1 plus I and 1 minus I. So those are going to be our two eigenvalues. And then we can use those to find the eigenvectors. So let's say eigenvectors for lambda equals 1 plus I. What do I have? Well, my matrix is 1 minus 1 plus I, because it's 1 minus lambda. And then negative 1, 1, and 1 minus 1 plus I. I can simplify those diagonals as a negative I in both cases. Acting on x1, x2 is going to give me 0, 0. If I look at the first row that comes out of this, that's going to be negative I x1 minus x2 is 0. The second row is redundant, as it always is. I can solve this for x2 to give me negative I x1 is equal to x2. That's my relationship. So my vector x, corresponding to 1 plus I, is going to look like x1, x2, or in other words, it's going to look like, since x2 is negative I x1, I have x1 negative I x1. And I can let x1 be 1 to give me my vector a little bit more cleanly. 1, negative I. So that's my first vector. My second eigenvector for lambda is 1 minus I. My matrix is going to become, instead of minus i's in the diagonals, it's going to become positive i's in the diagonals, and I'll have minus 1 and 1 against x1, x2 equals 0, 0. And the first line is going to give me I times x1 minus x2 is 0, or in other words, x2 is I x1. Could also divide by I and say that x1 is negative I x2. Either one is perfectly fine. This is telling me that my vector, corresponding to 1 minus I, is going to be x1, x2, or both in terms of x2. x1 is minus I, x2, and I can let x2 be 1 to give me my vector corresponding to 1 minus I as negative I and 1. This then tells me that my diagonalization, so my matrix 1, negative 1, 1, 1, can be diagonalized as my two vectors next to each other, which is 1 and negative I and 1, against a diagonal with the eigenvalues. My eigenvalues are here, 1 plus I and 1 minus I. So I have 1 plus I and 1 minus I. And then the inverse. So I'm going to take the inverse of x, which will be the 1 divided by the determinant. AD is 1 minus BC is minus a positive I squared. So 1 minus negative 1 is just going to give me 1/2. And then I'll have swapping A and D and making B and C negative, I have I and I. So that's my diagonalization, which immediately helps me produce this object, e to the t, 1, negative 1, 1, 1. I keep x and its inverse around, and I take the exponential of the diagonal. So this is e to the t times 1 plus I, e to the t times 1 minus I, and then 0 and 0. And I have a 1/2, 1, I, 1. And I have to go through the work of multiplying this all out. So this is kind of the worst part, is always this multiplication at the end. It's never the end of the world, but it's just a little bit annoying. So I'm going to do rows against columns in the first case. That's going to give me e to the t 1 plus I, and then it's going to give me on the top right negative I e to the t 1 minus I. Bottom left gives me negative I e to the t 1 plus I. Bottom right gives me e to the t 1 minus I. That multiplies the last term of 1/2, 1, I, 1. And what I'm left with, when I perform one more round of rows against columns, I'm left with e to the t times 1 plus I, and then I have I times negative I, those cancel, I get e to the t 1 minus I. I then have in the top right I copies of e to the t 1 plus I, and I have negative I copies of e to the t 1 minus I. I then have negative I copies of e to the t 1 plus I, and I have I copies of e to the t 1 minus I. I have negative I squared, so positive 1 copies of e to the t 1 plus I, and a positive 1 copy of e to the t 1 minus I. And there's a 1/2 sitting out front. This is a perfectly manageable answer if you want to stop here. Just for the matrix exponential, not for the problem. But you could complete the problem with this matrix exponential. But let's just go back to Euler's formula. And in particular, we're calling the following two, cosine of t, and maybe I'll start writing it as cosine of omega t. We often use the lowercase omega, which looks like a W. to determine frequency, this is e to the I omega t plus e to the minus I omega t all over 2. And sine omega t is e to the I omega t minus e to the minus I omega t all over 2i. And because of those two, if I go ahead and simplify this a bit, I'm going to pull an e to the t out front. And the reason is that there's an e to the t there, e to the t there, e to the t there, e to the t there. I'm looking at the 1 in the parentheses, by the way, so I'm highlighting specifically the 1 in the parentheses, and the rest is going to come along for the ride. So every term has e to the t. I'm actually going to pass the 1/2 inside to all 4 terms. And when I pass the 1/2 inside, I have e to the I t plus e to the minus I t over 2. I have e to the I t minus e to the minus I t, and then there was really an I in the numerator, so I can put it in the denominator at the price of a negative sign. So at the cost of that negative sign, I can put the I in the denominator. Same case on the bottom left. I have e to the I t minus e to the minus I t, and I can put the I in the denominator at the cost of a negative sign, but there's already a negative sign there. And then in the bottom right, I have e to the I t plus e to the minus I t over 2. And so what we actually see is cosine here and here. And we see sine here, really a negative sign, but not sine there and sine there. And so we can definitely simplify this expression if we want to, which just makes future calculations easier, as cosine t, negative sine t, cosine t. At this stage, we're not done. We've just found our matrix exponential. If we go back to our solution, there's the matrix exponential, but it multiplies 1, negative 1. So we have to go ahead and multiply this by the vector 1, negative 1. Now multiply by initial vector, which was 1, negative 1, to get our solution. Y as a vector, dependent on time, is e to the t, and then we have cosine t, negative sine t, sine t, cosine t. On the initial vector 1, negative 1, we're looking at all rows against all columns, all rows against all columns. That's going to give me e to the t, and then the top row against the column is cosine minus negative sine, also known as plus sine, and then the bottom row is sine minus cosine. And if I want to distribute e to both terms, I sure can, and call this e to the t cosine t plus e to the t sine t, e to the t sine t minus e to the t cosine t. So that's my solution in terms of a vector. But maybe if I want to write it in terms of just y1 and y2, I'm going to go ahead and read off the vector horizontally. So y1 will be the first row of the vector, e to the t cosine t plus e to the t sine t, and y2 will be the second row, e to the t sine t minus e to the t cosine t. And this is the true solution to the original ODE all the way at the top. True solution to this ODE. Let's do one more example, and like I said, this is going to be a slightly different example than what we've been noticing so far. So in this example, let's consider x prime and y prime. This is just as common as doing x1 and x2 or y1 and y2. Not really a big deal, but we'll see what's different in a bit. So we're going to say that x prime is equal to negative 2x plus y, and y prime is equal to negative 2y. And then maybe x at time 2 is equal to 2, and y at time 2 is equal to negative 2. If we go ahead and convert this into a vector form, just make a choice over x or y, which one you want to call the vector. Let's just call the vector. You know what? Let's go ahead and call the vector z, because there's an x and a y there, and we want to use something else for our vector. So we'll use a z. What should the matrix be here? Well, let's look at the coefficients. We've got a negative 2 on x, a 1 on y. There's really a 0 on x going on there, and then a negative 2 on y. So we're really looking at a matrix with coefficients negative 2, 1, 0, and negative 2. And this acts on z, where vector z is equal to x, y individually. Then we can say z at time 2 is equal to the vector, and I'm looking there, 2, negative 2. No problem. And we get that our solution, we still recover that the solution is still z as a vector of time is e to the t minus, now the initial time is a little different, so t minus 2 times the matrix -2, 1, 0, -2, acting on the initial vector to -2. If we want to calculate the exponential of this matrix, it's really no different. So e to the t minus 2 on a matrix M is going to be, you take the diagonal matrix and you just put a t minus 2 there instead. So that's not really the tricky part here. The tricky part is going to be when I try to diagonalize M. So let's go through the process of diagonalizing -2, 1, 0, -2. So we need eigenvalues. And if we do our determinant of -2 minus lambda, 1, 0, and -2 minus lambda, we recover -2 minus lambda squared minus 0, because it's 0 times 1, and this has to be equal to 0. So I get -2 minus lambda squared is 0, or I can take the square root of both sides. I get -2 minus lambda is 0. I can bring lambda to the right-hand side, and I see that lambda is equal to -2. At which point, if I look for an eigenvector, I only have one choice. I only have the choice lambda is -2, in which case my eigenvectors take the form -2 minus -2, which gives me a 0, and then I have a 1, 0, and then -2 minus -2 gives me another 0, against x1, x2 equals 0, 0, and this immediately gives me that 0 copies of x1 plus 1 copy of x2 has to be 0, and 0 copies of x1 plus 0 copies of x2 have to be 0. Well, the second line is superfluous. That doesn't mean anything. The first line, however, tells me x2 is always equal to 0, and I recover that my eigenvector corresponding to lambda being -2 is x1 and 0, because x2 has to always be 0, or if I let x1 always be equal to 1, I just have the vector 1, 0. And so I only have one eigenvector, which is bad because it means I'm not diagonalizable, right? Because the span of this one eigenvector is 1, 0 is not equal to R2, the domain of -2, 1, 0, -2. So the domain of my matrix is bigger than the span of my eigenvectors. The span of the eigenvectors is called the eigenspace, by the way. But the span of the eigenvectors is too large, or too small, for the domain, which means I'm not diagonalizable. So what do I do instead? I'm going to claim that I can still calculate this for you. Claim we can still calculate e to the t minus 2 m. And the way we do this is as the following. Recall that e to the x is equal to this series, x to the n divided by n factorial. This was a Taylor series problem that we completed. This is by Taylor series. So that means if I'm evaluating at t minus 2 times a matrix, I'm going to plug t minus 2 times a matrix in for x there, and I end up with the following infinite series. T minus 2 times a matrix to the nth power divided by n factorial. So I could write out the matrix then. I could do e to the t minus 2, and what was my matrix here? It was -2, 1, 0, -2. Let's write this out. Let's write this summation all the way out and see what happens. We've got t minus 2, and then the matrix -2, 1, 0, -2 to the nth power divided by n factorial. What we end up having is a sum of, really, I should write it like this, and goes from 0 to infinity, the matrix to the nth power, and then I'll just write t minus 2 to the n over n factorial. And let's go ahead and compute these objects. Let's see if we can compute these just by doing a few of them. -2, 1, 0, -2. Let's go to the 0 power. That's the identity. It always is. Not too bad. To the first power, it's itself. Everything else to the first power is itself. Let's look at it to the second power. So when we square it, we're going to multiply it by itself. And multiplying by itself, I have all rows against all columns. And so in the top left, I'm going to have a +4. In the top right, I'm going to have a -2. In the bottom left, I'm going to have a 0, and in the bottom right, I'm going to have a 4. So I have 4, negative 2, 0, 4. Let's do it again. Let's cube it. And so cubed, I'm going to have 3 copies. But I did just calculate the first 2 directly above. And so really I've got this 4, negative 2, 0, 4, and then I have another copy here, negative 2, 1, 0, negative 2. And let's go ahead and compute those, all rows against all columns. That's going to give me 4, negative 2, gives me negative 8 in the top left, and then in the top right I end up with a positive 4. In the bottom left I end up with 0, and in the bottom right I end up with negative 8. Do we see any patterns here? What's actually happening? 1's going to negative 2, 2's going to 4, or negative 2's going to 4, 4 is going to negative 8. And that's occurring in this bottom term too. Meanwhile, the bottom left term is always 0, so I certainly always have zeros in the bottom left. And then the top right term is 0 going to 1, but let's pretend that we just started at 1 instead. Pretend we start at 1, we go from 1 to negative 2, from negative 2 to 4. All we have in each of these cases of negative 2, 1, 0, negative 2 to the nth power, the diagonals are occurring to the nth power. The bottom left is always 0, and then the top right is equal to negative 2 to the n minus 1 power so long as n is greater than or equal to 1. So there's the 0 case where that top right term was 0, and it's not, negative 1/2, but in every other case, we have exactly this property. So let's go ahead and use this as the calculation for the powers in our exponential series here. So we can calculate the matrix exponential series now because we found what the powers actually look like. The powers actually look like, so e to the t minus 2m is the sum, and I've just calculated my powers as negative 2 to the n, negative 2 to the n minus 1, 0, and negative 2 to the n, and then t minus 2 to the nth power over n factorial. And this only occurs when n starts at 1 to infinity, and then we add the identity, which was the 0 case. But what we can do with this is we can go ahead and apply it to each entry here, the summation, and we find out that on the entries, I have something like this. I have n equals 1 to infinity, negative 2 to the nth power, t minus 2 to the nth power over n factorial. So I'm also bringing these into all 4 terms. I have the sum n equals 1 to infinity of negative 2 to the n minus 1, t minus 2 to the nth power over n factorial. I have 0, still a bunch of copies of 0 there. And then finally I have a sum of negative 2 to the nth power, t minus 2 to the nth power over n factorial, and goes from 1 to infinity. And I'm adding this 1, 0, 0, 1 to the end. But I can go ahead and add my 1 to the first term and my 1 to the last term. What I end up with is the following. I have the sum n equals 0 to infinity, because in fact the 1 that I'm adding is equivalent to the 0 case there. Negative 2 to the n, t minus 2 to the n over n factorial. In the top right, nothing's changed. N starts at 1 and goes to infinity. Negative 2 to the n minus 1, t minus 2 to the n over n factorial. Then I have a 0, and I have a sum n equals 1, actually 0 now to infinity, because I've added 1 to that term. Negative 2 to the n, t minus 2 to the n over n factorial. And what I can actually do is I can perform some of that re-indexing. So I can re-index the sum. And if I re-index the sum in a very clever manner, this ends up being, well, what is this sum, first of all? That sum is an exponential to a power negative 2, t minus 2. This is the same. This is the exponential to a power negative 2. It's this power, t minus 2, just by the Taylor series. I can re-index in the top right. Re-indexing in the top right, I can send this to a t minus 2 out front, and then I can send it to n equals 0 to infinity, negative 2 to the n, t minus 2 to the n over n factorial. I don't expect any of you to know how I actually did that, but this is also e to the negative 2 t minus 2, but there's this t minus 2 that came up front. And so what do my four terms become? They become e to the negative 2 t minus 2, t minus 2 e to the negative 2 t minus 2, and e to the negative 2 t minus 2. This is the matrix exponential e to the t minus 2 of negative 2, 1, 0, negative 2. And I don't really expect any of you to be able to reproduce this. I just wanted to show you that it's possible to actually calculate these in a non-diagonalizable setting. Let's go ahead and finish our problem. We just computed that. We need to multiply by our initial vector. So we still need to multiply by the initial vector, which was 2, negative 2, I believe. I should scroll up and make sure I didn't get my negative sign in the wrong spot. 2, negative 2 it was. And so we go ahead and actually compute that. Our solution, z as a function of t, is what I've calculated, that matrix exponential, e to the negative 2 t minus 2, and then t minus 2 e to the negative 2 t minus 2, 0 e to the negative 2 t minus 2, against the initial vector 2, negative 2. I'm looking at all rows against all columns. That's going to give me 2 copies of e to the negative 2 t minus 2 minus 2 copies of t minus 2 e to the negative 2 t minus 2 in the first row. And in the second row, I'm going to have 0 copies, 0 times 2, and then negative 2 copies of e to the negative 2 t minus 2. I can go ahead and simplify the top row if I want to a little bit. It looks like I have a total of 6 copies. There's a negative 2t term. And then I've got 6 copies without the t, because I have 2 minus 2 copies of negative 2. So if I want my original x and y, x is a function of t, y is a function of t, I'm just going to read off my solution row by row. X will be the first row, negative 2t, I could really call it negative 2t plus 6, and just factor out e to the negative 2 t minus 2. And then y is going to be negative 2 e to the negative 2 t minus 2. That's the true solution to the ODE. It's a little bit trickier. Like I said, I'm really not going to make you work with non-diagonalizable matrices, and hopefully you can appreciate why it's really useful if we do encounter diagonalizable matrices. A little fun fact and teasing for the future, in quantum mechanics, they're always diagonalizable. So aren't the physicists lucky? Us mathematicians have to work with the crappy matrices, but the physicists get the good ones. So we're going to see why that's the case in a few days. I'll see you then. Bye.